Hello, I'm Rebecca Barnes and welcome to the Science ESA vodcast. In this episode, our journey leads us to the small bodies of the solar system. We'll investigate comets and asteroids and find out about Europe's pioneering missions launched to explore them. About 4.5 billion years ago, the Sun formed from a collapsing cloud of gas and dust and ignited into a fully fledged star. Leftover material was blasted away, the bulk of which settled into a disk that eventually accreted into the planets and moons that we see today. Most of the mass of the solar system is contained within the Sun, planets and moons. The remaining mass is distributed among billions of smaller objects that were not embedded into larger bodies during the early history of the solar system. While most of these inhabit the outskirts of the solar system, forming the Oort cloud, many can also be found in the inner regions between or just beyond the planets.
Well over 1 million small bodies, some of them only chunks of rocks, lie in the region between Mars and Jupiter, and are perhaps the remnants of a planet that never formed. Within the disk of material surrounding the young Sun, as protoplanets began to take shape, the giant planet Jupiter is thought to have formed quickly. Its large mass, and therefore large gravitational field, pulled and pushed the material between itself and Mars, changing the orbits of the small bodies in what is now known as the main asteroid belt. Consequently, the material in the main asteroid belt was never able to form into a planet. Further out in the solar system, beyond Neptune, in a region known as the Kuiper Belt, there are about another 100,000 of the leftover building blocks of planetary formation. Occasionally, gravitational disturbance caused by Neptune and Uranus can draw one of these bodies out of the Kuiper Belt and into the inner solar system to become a short-period comet. The solid nucleus of a comet is usually between a few hundred meters and some 20 kilometers across. It resembles an icy mud ball that is made up of dust grains that have been embedded in ice. As a comet approaches the orbits of Saturn and Jupiter, it starts to become active. Heated by the Sun, the ice in the comet sublimes. Jets of gas and dust begin to shoot out from the nucleus, forming the coma, a giant cloud of the emitted gas and dust that surrounds the comet nucleus, spreading out for hundreds of thousands of kilometers. As a comet travels closer to the Sun, gas and dust tails begin to form. Ultraviolet light from the Sun ionizes gases in the coma. These ionized particles are then dragged away from the comet by the solar wind, forming the plasma or ion tail. The dust tail is formed when solar photons collide with dust in the coma. Both tails stretch out for millions of kilometers. Comets that approach the Sun from the Kuiper Belt are known as the Jupiter family of short-period comets. They usually take just 4 to 10 years to orbit the Sun, and they lie very close to the ecliptic, the plane on which the planets orbit. The Kuiper Belt is one of the 2 known comet reservoirs. The other is the Oort cloud, a spherical cloud of icy objects that surround the Sun and the planets. Comets from this region of the solar system orbit the Sun from a variety of angles. They are not confined to the ecliptic plane. The comets in the Oort cloud are mostly long-period comets, with periods greater than 200 years. However, comets with shorter periods may also originate from the Oort cloud, such as Comet Halley, for instance.
Today it is thought that the objects that now populate the Oort cloud actually formed much closer to the Sun. However, through gravitational interaction with the giant planets, in particular Uranus and Neptune, they were slung outwards to the fringe of the solar system. Comets that originate from the Oort cloud are thought to be disturbed by gravitational interactions from passing stars or molecular clouds, causing them to change orbit and head into the inner solar system. The combined mass of all known asteroids and comets is fairly insignificant in terms of the total mass of the solar system. However, they are primitive objects that have changed very little over the last 4.5 billion years. Comets and asteroids hold a record of the physical and chemical processes and conditions present in the early solar system.
As the disk of material surrounding the newly formed sun began to cool, the leftover gas and dust started to freeze, trapping within them information about the young developing sun. This reservoir of pristine material is still retained today because comets and most asteroids are too cold and too small to undergo geological activity. The main processes that have permanently altered larger solar system bodies, such as the planets.
Studying comets and asteroids provides important clues about how the solar system formed and about the origins of the chemicals vital for life to start on Earth. These essential seeds for life may have originated in comets and been delivered to Earth during impacts early in the history of the solar system. In 1986, Comet Halley made its first approach to the Sun since the beginning of the space age, providing a unique opportunity for the comet to be studied close up and in more detail than ever before. Joining the international effort to examine this famous comet, Europe launched its pioneering deep space mission, Giotto.
During its flyby of Comet Halley, Giotto withstood a harsh battering by dust particles in the coma and took the first ever close-up images of a comet nucleus. The unexpectedly dark surface observed by Giotto suggested that Comet Halley was covered in a layer of dust. Great jets of gas and extremely fine dust were observed shooting out of the dark nucleus. Water vapor accounted for most of the volatile material detected, along with substantial quantities of carbon monoxide, carbon dioxide, methane, and ammonia.
The data returned by Giotto showed that the comet was rich in mineral-forming elements, meaning that the history of comet formation was more complex than previously thought. The data also showed that Comet Halley had a similar relative abundance of light elements as the Sun. This means that the material the comet is made from has remained unchanged since the planets formed about 4.5 billion years ago. This material existed in the cloud of gas and dust from which the solar system formed. Following the successful encounter with Comet Halley, Giotto targeted a second comet for detailed study, Comet Grigg-Skellerup. During this extended mission, Giotto became the first deep space mission to use a gravity assist from Earth to change its orbit, the first spacecraft to be put into hibernation, and the first to fly just 200 kilometers from a comet's nucleus. Shortly after Giotto had achieved its flyby of a second comet, Europe gave the go-ahead for the development of Rosetta, an even more ambitious and unique expedition to another tiny icy world. The Rosetta mission is an international collaboration between scientists from across Europe and the United States. In 2004, packed with a suite of 11 scientific instruments and a small lander, Rosetta set off on a 10-year journey to meet with Comet 67P Churyumov-Gerasimenko. Comet 67P Churyumov-Gerasimenko is a Jupiter family comet that takes just 6.6 years to orbit the Sun. It is a tiny world with a nucleus that is just 4 kilometers across. In preparation for the Rosetta mission, Comet 67P has been observed using ground-based observatories and space telescopes. However, the real nature of this comet will remain uncertain until it is visited up close. Rosetta will be the first spacecraft to enter into orbit around a comet, and the first to observe from close proximity how a comet's activity develops as it heads towards the inner solar system. The Rosetta spacecraft also carries a small lander called Philae that will attempt the first ever controlled landing on a comet nucleus.
Once launched, Rosetta needed to gain velocity to match that of the comet at the rendezvous in order to be able to go into orbit around the comet's nucleus. To achieve this, Rosetta spent the first half of its 10-year journey hurtling around the inner solar system. The spacecraft flew close to both Earth and Mars, using their gravity as a slingshot to increase velocity before heading out to Jupiter's orbit, where it will meet Comet 67P. Just before Rosetta's final slingshot around the Earth in 2008, the spacecraft flew through the main asteroid belt and, exactly as planned, had a close encounter with asteroid Steins. This was a good opportunity to get a close-up view of this rare asteroid and also test out some of the science instruments on board the spacecraft. Data taken by Rosetta's instruments confirmed that this asteroid belonged to the rare E-type class, and images revealed Steins to resemble the shape of a brilliant cut diamond. The data also showed that asteroid Steins is not a solid body, but is severely fractured. A past impact shattered this asteroid and reduced it to a loosely bound pile of rubble. Entering the asteroid belt for a second time, en route to the outer solar system, Rosetta made a second asteroid flyby, this time past asteroid Lutetia. Racing past the asteroid at 15 kilometers per second, Rosetta's scientific instruments were used to study the largest asteroid yet to be approached by a spacecraft. In the first close-up images taken by Rosetta, Lutetia appeared to be a battered, heavily cratered world and is a survivor from the violent formation of the solar system. The first results from this flyby have shown that Lutetia has a similar surface texture to Earth's moon. This asteroid has been pulverized by past impacts, resulting in a thick blanket of debris covering the surface, with images showing boulders rolling down crater walls.
Rosetta is the first spacecraft to travel so far from the Sun, powered only using solar arrays. Following one final maneuver in deep space, Rosetta will spend the ultimate leg of its journey to the comet in hibernation, to limit consumption of precious power and fuel. In May 2014, Rosetta will be woken, ready to rendezvous with Comet 67P. Inserting the Rosetta spacecraft into orbit around the comet will present one of the greatest challenges of the mission. Rosetta will slowly make its way into orbit through a series of complex maneuvers, gradually adjusting the spacecraft's velocity to match that of the comet. As the spacecraft gradually approaches the comet, the Rosetta team will ensure that the spacecraft's camera can view the nucleus with the best illumination possible from the Sun. The first images will dramatically improve calculations of the comet's position. This information will help fine-tune the maneuvers that will insert the spacecraft into orbit. The continuously changing comet makes planning and performing the necessary science experiments extremely challenging. Rosetta is a very dynamic mission with very dynamic operations. In preparation for the time when Rosetta will accompany Comet 67P into the inner solar system, the Rosetta team has already started planning the measurements that each individual instrument will take. To make the most of this remarkable event, the team must determine how the entire scientific payload can work together, so that as much information as possible can be extracted out of the measurements. The orbiter contains an entire laboratory of instruments that combine multi-wavelength remote sensing techniques and direct or in situ sensing systems to create as complete a portrait of the comet as possible. From orbit, Rosetta will have a three-dimensional view, and for approximately 18 months will watch and measure what happens as the comet is gradually heated by the Sun.
The surface of the nucleus will be described in detail at ultraviolet, optical, infrared, and submillimeter wavelengths, which will provide clues to its chemical and mineralogical composition. The camera system will map the nucleus in high resolution to determine details of the surface topography, as well as its size, shape, and how it is rotating. As well as this, the camera system will monitor changes taking place on the surface of the nucleus due to the sublimation and erosion processes. All this information, together with data taken by the other instruments, will help to figure out how comets become active and the nature of comet activity. Measurements made at infrared and submillimeter wavelengths will focus on identifying minerals and molecules present in the material of the comet's nucleus and coma. In addition, a temperature map will be made of the comet nucleus. The mass, overall density, and the basic structure deep in the comet's interior will be determined from measurements made at radio wavelengths using a variety of techniques. The comet's atmosphere, or coma, will be analyzed in situ by taking key measurements of the density and composition of the gas and dust from which it is formed. The composition will provide a clue to the evolutionary history of the material in the pre-solar nebula. In addition, individual dust particles will be investigated from microscope images, and the plasma environment of the comet and its interaction with the solar wind will be monitored in situ. A few months after Rosetta has entered into orbit around the comet, whilst the nucleus still has little surface activity, the lander Philae will be released onto the surface of the nucleus. Landing on a comet is very different to landing on a planet or moon due to the comet's weak gravitational field. There is no fear of crashing into the surface. The challenge is to stop the lander from bouncing away again. During this first ever controlled landing on a comet, the 3 legs of the lander will dampen out most of the kinetic energy to prevent it bouncing, and in parallel, a harpoon will anchor the lander to the surface. Philae will perform the first ever in situ analysis of the material that constitutes a comet nucleus and take a full panoramic image of the area around the landing site. Sensors on board the lander will measure the thermal and mechanical properties of the nucleus and probe its electrical characteristics. A drilling and sampling system will collect subsurface samples down to a depth of about 20 centimeters. This material will be distributed to microscopes and ovens that will heat the samples to study the gas released with sophisticated gas analyzing instruments. These experiments will investigate the structure and composition of the material that forms the nucleus, which is expected to contain a significant amount of organic matter, the essential chemical seeds for life.
Eventually, Rosetta and its lander Philae may succumb to the immense amount of dust emitted energetically from the comet as it passes the Sun. By December 2015, the spacecraft and the comet will have circled the Sun and be on their way out of the inner solar system. Meanwhile, the wealth of data taken remotely and in situ will be combined to build a picture of the structure and composition of Comet 67P, determine the age of material from which it formed, and understand the processes that drive comet activity. The Rosetta mission has been designed to gather enough data during this unique opportunity to comprehend the nature of the life cycle of a comet. The data from Rosetta will provide scientists with a window into a time in the early solar system before the planets existed. It will uncover further clues about the origin of the solar system and of our own planet. Just as the Rosetta Stone provided the key to an ancient civilization, the Rosetta spacecraft will unlock the mysteries of the oldest building blocks of the solar system. I'm Rebecca Barnes. Thank you for watching the Science ESA vodcast.